My name's Andrea, and I work at the Ann Arbor Hands-On Museum and Leslie Science and Nature Center. You just caught me in my chemistry lab. Do you want to do some chemistry with me today? See, chemistry is the study of matter, and that's pretty much everything around us. Anything that has mass or takes up space is matter. Chemists study a lot of stuff. What do you think of when you think of chemistry? Do you think of mixing things together? Or maybe blowing stuff up? Today I'd like to do a few chemistry experiments, and most of the supplies that you'll need you can find inside your house. You can either watch me do them and do them later, or do them right along with me. One big idea that chemists like to talk about are physical changes versus chemical changes. A physical change is when something changes form or shape. Like, for example, I have this ice cube and it's cube-shaped. But if I mix it with sunlight or heat energy, then it becomes like this, puddle-shaped. The stuff that's in the bag, the matter, is the same. It's still water in either case, but it's shaped differently. This is an example of a physical change. Now, a chemical change is slightly different. That's where something new is created when you mix two substances together. Let's do a few experiments to see if we notice any physical changes versus chemical changes. Now, for my first experiment, I need a little bit of fluff. This is what you might use if you're making a teddy bear, a stuffed animal, or a pillow. Now, scientists, remember, it's always important to be safe when doing your experiments. So I'm going to wear my safety goggles, even though I know that for this experiment, there's nothing dangerous involved. I'm going to start our first experiment by stretching the fluff. See what you notice happens when I do this. Use your senses to make observations. I notice that my fluff is getting longer and that there are more holes in it, so I can kind of see through it. It's also spreading out. Now, since I know the ingredients in this first experiment are safe, I can also use my other senses, like smelling or feeling or hearing. But don't use your sense of taste. Save that for lunch. All right, so if I smell it, it doesn't smell any different than when I started. Or if I listen to it, I don't hear any sounds. And if I feel it, it feels like fluff. So when I stretch my fluff, do you think that's a physical change or a chemical change? Make your hypothesis or your good guess about what you think. Yep, it's a physical change. The fluff looks different, but it's the same matter. It's still just fluff, and nothing new has been created. Let's make a chart to write down our observations about physical and chemical changes. So far, we have that physical changes might change shape. Okay, for my next experiment, I'm going to add a container of water. Now, when I mix my fluff with my water, do you think that'll be a physical change or a chemical change? Remember, a physical change is when the shape might change, but a chemical change is when something new is created. All right, make your prediction, physical or chemical, and then let's try. Here we go. What did you notice happened this time? So I noticed that my fluff soaked up the water and it sunk down to the bottom of my container. And I also noticed that it smells the same as before and it's still not making any sound. If I touch it, it feels pretty much the same, just a little wetter. Now, another way to notice a physical change from a chemical change is to see if you can separate the materials back out from each other. Because remember, in a chemical change, something new is created. So, do you think we can separate out my fluff from my water? Sure, yeah, I can just take it out, right? And my fluff is a little wetter, but I still have fluff and water. And actually, if I let this fluff dry for a little bit, then I would have the same things I started with. So what do you think? Physical change or chemical change? Yep, this one's another physical change. Great job, scientists. Okay, let's write down our observation that in a physical change, you can separate the materials back out and still get the two ingredients that you started with. Okay, for our next experiment, I'm going to mix some water with some salt. What do you think this time? Is it a physical change or a chemical change? Will something new be created when I mix these two things together? Or can I separate them back out? All right, got your prediction? Let's try it. What do you notice when I mix these things together? I noticed that the salt sunk down to the bottom at first, and then when I stirred, it kind of spread out. And now it looks like the salt is dissolving towards the bottom, and it's kind of getting a little bit clearer down there. What about our other senses? Still smells like salt and water, and doesn't make any sounds. Feels the same as before. What do you think? A physical change or a chemical change? Do you think we could separate these materials back out from each other so that I could get salt and water separate again? This one's actually a physical change. Even though the salt dissolves in the water and the sodium and the chlorine break apart, it's still just water and salt. And I actually could separate them back out. All I would need to do is boil the water and I'd be left with salt, or I could let it all evaporate and I'd be left with salt at the bottom of my glass. All right, ready for the next experiment? This time we're gonna mix baking soda with lemon juice. I don't know if you can see it in there. Again, we're looking for evidence of a physical change or a chemical change. All right, ready? Whoa! What did you notice? Well, with my sense of sight, I noticed lots of bubbles forming. And with my sense of smell, it still smells the same, lemon juice and baking soda, but I could hear the fizzing sound. And it feels kind of bubbly. All right, what do you think? Physical change or chemical change? Was something new created this time? What's your prediction? If you said chemical change, you're right. Lemon juice and baking soda mix together and they make carbon dioxide gas, which is what filled the bubbles that we saw. Okay, let's add to our chart that evidence of a chemical change is you might see bubbles or hear fizzing. Okay, for our next experiment, scientists, we're going to need a few things. Some vinegar, some more baking soda, a measuring scoop, a balloon, a bottle with a narrow neck. You could use like an old pop bottle, works great for this experiment. This is just a scientific bottle. And then if you have a funnel handy, that is useful, but it's not necessary. All right, scientists, don't forget your safety goggles either. Now, the first step to this experiment is to fill your balloon with a couple tablespoons of baking soda. This is where the funnel comes in handy. You can do it without a funnel, it just might be a little bit messier. All right, so I'll take my scoop and fill up baking soda. Make sure it goes down into the balloon. Sometimes you'll need something to poke it through if it gets stuck in the funnel. So I'm just going to use this pipette. All right, now that that's done, I'm going to take my balloon off my funnel and set that aside for later. Next, I need to take my vinegar and fill my bottle with it. So I'm going to carefully pour it into my bottle. I have about 1/4 cup of vinegar in here, but it doesn't need to be exact. Perfect. Okay, next I need to stretch the mouth of the balloon over the mouth of the bottle. This part can be a little tricky, so if you have a grown-up around or another sibling, then you can have them hold the bottle for you so that it doesn't tip over when you stretch the balloon on top. All right, for the last step of our experiment, in a second, I'm gonna flip the balloon up so that the baking soda drops out of the balloon and into the container. Now remember, we're looking to see if it's a physical change or a chemical change. So look and see what happens in the bottle, but also what happens in the balloon. Okay, are you ready? Whoa! Very cool. What did you notice? Well, I noticed some bubbles being formed, and I can hear them fizzing in the bottle. And I also noticed that my balloon got a lot bigger. It inflated with something. Do you think this is a physical change or a chemical change? What evidence do you have? If you said chemical change, you are correct. The balloon inflated with carbon dioxide gas, which is what these two ingredients made when they got mixed together. And we saw bubbles and heard fizzing too, which is on our chart for evidence of a chemical change. You know what I'm ready for? A movement break. Take 30 seconds or so to jump up and down or run around or stretch so that you're ready for some more science. Oh, sorry, I was getting a snack. I mixed some cereal with some milk. Do you think that's a physical change or a chemical change? Cereal and milk is one delicious physical change. But actually, when you eat it and your body starts to digest the food, then it becomes a chemical change. Your body turns the cereal and milk into nutrients that you can use to run and jump and play. Okay, now that we're pretty good at deciphering physical changes from chemical changes, let's do another experiment to discover more evidence of a chemical change. For this experiment, I'm going to mix together some yeast, which is a fungus that we usually use when we're making bread. It's actually alive and it converts the sugar in your bread dough into gas, which is what makes your bread rise because of the bubbles. And then I'm also going to use some hydrogen peroxide, which is what you would use if you had a cut or a scrape or maybe a canker sore in your mouth to disinfect it and clean it. And lastly, I'm going to use a thermometer for this experiment because I want to track the temperature in my mixture. So I'm going to start by pouring in a couple tablespoons of hydrogen peroxide into my glass. Okay, and then I'm going to put in my thermometer so I can read the temperature at the start of my experiment. You want to let it settle a little bit so that you get an accurate reading. So mine's at 79.2. All right, then I'm going to take a tablespoon of yeast and add it in and stir it up. Remember to watch and see what happens in your experiment. All right, ready? Here we go. Pour it in, and then I will mix it up. All right, let's watch and see what happens in our experiment. Whoa, what do you notice? I see lots of bubbles, and my experiment is rising, kind of like how we talked about how bread rises. It smells like yeast or bread, and I see lots of foam inside too. Remember how we took the temperature at the beginning of our experiment and it was 79.2? Now it's, whoa, 95 degrees. It's gone up a lot since we started our experiment. This is what we call an exothermic reaction. That means that when the chemical change is happening, it's releasing or converting some of that energy as heat. And that's why the temperature on the thermometer goes up. The opposite of this can also happen, and that's called an endothermic reaction. In an endothermic reaction, the temperature on the thermometer would go down because the chemical change absorbs the heat from its surroundings. Now, let's write down temperature change as more evidence of a chemical change. Okay, I want to do this experiment again, except I need a bigger table. For our experiment this time, we're going to use most of the same ingredients. Still hydrogen peroxide and yeast, but we're going to add some dish soap, some food coloring, and some warm water to our mixture. All right, I've already poured some hydrogen peroxide into my bottle here. You notice that I've picked a bottle that has a narrower top to it. That'll be good for our experiment. And then what I'm gonna do in my other container is I've got about 3 tablespoons of warm water in here, and I'm gonna add a few drops of food coloring so that it makes it a little bit more colorful. Not too many, just a few. I'll stir that around so they mix together. And then I'm going to add 1 tablespoon of my yeast. And I'm gonna stir it up for 20 to 30 seconds. Okay, now the next step is to take your dish soap and pour a little bit of dish soap inside your bottle. And then swirl it around so that they mix together. So I'm going to take my yeast solution and pour it into my bottle. And my safety goggles are on, so I'm good and safe. And then I'll take a step back so that I can see the reaction. What do you notice happening in our experiment? So I noticed bubbles, and the foam is still pretty warm, so we know it's an exothermic reaction again. But why are there so many more bubbles this time than there were last time? Well, it's because of the soap. So when you mix hydrogen peroxide and yeast, we know that it creates oxygen. And that oxygen gas gets trapped in the soapy layer that we added to the hydrogen peroxide. And soap's really good at making bubbles. So when you mix them together, it makes way more bubble solution than it did before. That's pretty cool. Some scientists will call this experiment elephant's toothpaste because it makes a lot of foamy stuff that looks kind of like toothpaste. And it's about the amount I imagine an elephant would need if they were brushing their teeth. But even though it's called toothpaste, scientists, remember, it's not really toothpaste, so don't eat your science experiment. Okay, let's head back to the lab because I've got one more sign of a chemical change that we haven't talked about yet. All right, the last sign of a chemical change that we'll discuss today is color change. And so for this experiment, you can do it at home too if you have some red cabbage, which actually looks purple. How confusing. Red cabbage has something called anthocyanin in it, which is a natural pH indicator. It tells you how acidic or basic something is. And you can mix it together with liquids from your house, like vinegar or lemon juice, which are acids, or baking soda solution and soap, which are bases. They'll react differently to the red cabbage juice, depending on if they're acidic or basic. What I'm gonna do is I'm gonna take some cabbage that I've chopped up and put it in a blender, and then I'm gonna add in some warm water. And I'm gonna blend it for a few seconds until I've made a cabbage smoothie. Gross. Now that it's blended up, I'm going to use this strainer to help me strain out any of the big chunks. You could also use a coffee filter if you had another person there to help you hold it up. Okay, perfect. Okay, Now that I have my cabbage juice blended up and strained, I can mix it with a couple different liquids that I have in my house to see if they're acids or bases. I've got a bunch of different glasses of different liquids here, and we'll go ahead and try mixing them together and see what happens. Alright, so this is just regular water that I got from my sink. When I add it to my cabbage juice, let's see what color it turns. Oh, don't forget your safety goggles. All right, so it stays kind of purpley in color, maybe a little bit bluish. The middle of the pH scale is what we call neutral, and that means it's not really acidic or basic. And water is one of the things that we consider neutral. Because it came from my sink and it's not distilled, it might be a little bit basic. It's a little bit bluish purple, but mostly right in the middle of the pH scale. All right, let's take a look at our next liquid. This next liquid that I have is vinegar. Vinegar we know is an acid, so let's see what happens when cabbage juice is combined with an acid. Ooh, it turns a bright pink or red color. That's pretty neat. So if our pH scale goes from 0 to about 14, and water is right in the middle at about 7, vinegar is going to be right around the 2 mark. It's pretty acidic, but not super strong. All right, next let's try some water mixed with baking soda. We know baking soda is a base, so I expect this to be a bit more purple or blue than our regular water. Ooh, that's pretty cool. It's pretty blue. And a little bit lighter in color than our purple water. It's hard to see in the video, but if a light shines through, then it's a little bit lighter in color. That's cool. All right, our next liquid is some lemon juice. Lemon juice is pretty acidic too. You can see that it turned pink, just like our vinegar did. It's another liquid that's probably around the 2 or 3 mark on the pH scale. I've got some soapy water. I just added a little bit of hand soap to this water, so let's see what happens. Ooh, interesting. This is surprising to me. I thought it would be more basic, but it actually looks like it's a little bit on the acidic side. I wonder why. That's a good thing for me to research a little bit later. All right, my final ingredient is, this is some window cleaner. So it has ammonia in it, which is a type of cleaner that's a base, typically. So I expect it to be pretty basic. Ooh, yeah, you can see that it turned kind of greenish in color, and that means that it's on the further end of the base side of our pH scale. So it's probably a bit more basic than our baking soda solution that we did before. That is pretty cool. I'll give you a close-up look of all of these liquids on the pH scale so you can get a better look. Now, I have a couple tricky examples that I want to show you too. If I have some water and I add some food coloring to it, do you think that is a physical change or a chemical change? It does change color, and that's one of our pieces of evidence of a chemical change. But this one is actually just a physical change. Even though it changed colors, I still just have food coloring and water. I didn't create anything new. It's just that the food coloring spread out through the water, so it changed the color of the water. It's kind of like when you use watercolors. If you use a lot of water in your watercolor, the color might be lighter than if you only use a little bit of water. The pigment spreads out through the water, and it changes what color it looks. So even though it changes color, it's still a physical change. Okay, I have another tricky one here for you. This is some dry ice. Dry ice is pretty cool. It's not like regular ice. It's not made of water. It's actually made of solid carbon dioxide. And it's super, super cold. It's so cold, in fact, that I have to wear my winter gloves when I hold it. Otherwise, it might hurt my hand. It's about 109 degrees below zero. Now, you can see in this dry ice that it's solid when I'm holding it, but you might be able to see a little bit of the fog coming off the bottom here. And that's because when dry ice heats up, it doesn't melt like regular ice. It actually does something different called sublimation. Sublimation means that it turns from a solid to a gas. Now, this is an example of a physical change because the gas coming off of the dry ice is still the same carbon dioxide that the solid is made of. It's actually invisible when it sublimates, but we can see it because water in the air condenses on it and kind of forms a cloud or fog, just like it does outside sometimes when it's early in the morning or it's raining. Now, I'm going to make this even trickier by adding it to some water. And I want you to observe what happens when I put the dry ice in the water, because the water is going to heat the dry ice up even faster than the air does. Ooh. That is pretty cool, right? You can see the sublimation happening. You can see the fog coming off of the water surface and out of the container. And you can also see some bubbles inside, right? Which is normally a sign of a chemical change. But actually, in this case, it's still a physical change. The carbon dioxide that's coming off of the dry ice when it sublimates is getting trapped in the water. And that's what's making the bubbles. Kind of like what we saw when we did the elephant's toothpaste experiment earlier today. The oxygen in the elephant's toothpaste was getting trapped in the soap bubbles. And in this case, the carbon dioxide is getting trapped in the water. That is pretty cool. And makes for a really good cauldron around Halloween time. All right, let's review the evidence we have for physical and chemical changes. For physical changes, you might notice that it changes shape or form. All phase changes like freezing or melting or vaporization, those are all examples of physical change because even though it looks different, the matter is the same. And you can also, if you're mixing two things together, you can separate out the ingredients again. So you have what you started with at the beginning of the experiment. All right, and for a chemical change, we know something new is created every time there's a chemical change. You also might see bubbles or hear fizzing. There might be a temperature change, like an endothermic or exothermic reaction. And I've added in here color change, like we saw when the pH changes. A pH change is always a sign of a chemical change. All right, scientists, I have one final thing to show you. And it actually doesn't have much to do with physical or chemical changes, but it requires dry ice. And since I already had to go pick that up, I wanted to show you because it's pretty neat. So I put my dry ice in this container, and I've got some bubble solution that I made earlier. It's just Dawn dish soap and water mixed together. And I've got a straw that I'm going to use to blow my bubbles. Now, normally when you blow bubbles, they fall to the ground because of the force of gravity. Gravity pulls everything to the earth, or to the Earth's surface anyway. And so the bubbles fall down towards the Earth's surface. When I blow the bubbles into the dry ice, watch what happens this time. They don't float down to the bottom because the dry ice that's sublimating inside the container is letting off that carbon dioxide gas, which is denser than the air. So it stays at the bottom of the container and the bubbles sit right on top of it instead of falling all the way to the ground. That is pretty cool. Scientists, thank you for joining me today. I hope you had fun. We'll see you next time. The last sign. I've lost my camera. Okay. I'm also going to use a thermometer, which I don't have. How am I going to do this on video? This next experiment, I'm going to mix together hydrogen peroxide. Nope, that's not hydrogen peroxide. Converts the sugar in your bread dough in... Shouldn't burp. Woo. This was bad. This was bad. This was bad. I'm sure I'm going to eat the rest of this.